Welcome to this What's New in ESAComp 4.6 webinar. My name is Harri Kataisto and I'm here with my colleague Andre Mörnicke. The first example shows how the thermal distortion of the fiber metal laminate can be simulated. This is caused by the curing and cooling down processes. The panel load type edge bending is part of the solution in this example. The second example illustrates the shell-based stiffeners and how they differ from the traditional beam stiffeners. The same example is used to demonstrate negative reserve factor in the buckling analysis. Then the use of shell-based stiffeners is demonstrated to form closed profiles. ESAComp example case 41 mimics the study performed in the European research project. The behavior of the stiffened curved composite panel is complex, involving multiple modes of buckling before the final global buckling mode shape takes place. This panel was actually a validation structure to study the limits of the various software tools, and ESAComp performs very well. Results predicted with the ESAComp are shown with the red dots on top of the experimentally measured load versus end shortening curves. In the final part of my presentation, I'll focus on the composite pressure vessels. Enhancements related to the composite pressure vessels modeled with shell elements are described. Also, the new model, which is based on the 3D solid elements, is shortly highlighted. Before going to the actual demonstration, Andre can shortly tell what he's going to talk about towards the end of this webinar.
So hello also from my side. Thank you, Harri, for the introduction. Just a few comments about the two topics that I'm going to cover. First one is ESAComp HyperWorks post-processing interface, the way it's used at the moment with the current ESAComp version and HyperWorks 14 latest patch. And last but not least, we have introduced Python scripting in the new ESAComp version, and I'm going to tell a little bit about how to get you started and what are the capabilities, what you can do with it. That's it from my side, and I hand back to Harri for the first part of the live demo.
Okay, so I will start from the first example case. This demo contains multiple short demos, and the first example shows how the thermal distortion of the fiber metal laminate can be simulated. And this is caused by the curing and cooling down processes, and the analysis is performed with the combination of the laminate and panel analysis. I will now go to ESAComp. And I will take the example case 45 from the database. I have here 4 laminates. I'm going to use the first one. I will go to modify the laminate, and what I need to do after laminate's layup specification, I need to define a reference environment where the laminate is stress and strain free, and here I define the curing temperature. Then I need to define a laminate load, which is the analysis environment, and now the room temperature is defined here, and consequently we have a thermal delta T of minus 100 Celsius as a thermal load. Then I make a simple laminate analysis with the combination of the laminate and the thermal load, and I pick this results item here, laminate stress and strain state numerical results, and from the content drop-down menu I pick the full, and as a result of this analysis I will get equivalent thermal forces and moments, which are these forces and moments here. So these equivalent thermal forces and moments, they produce to the laminate the same strain level as the thermal load. Now we have in ESAComp a new load type for the panels, that's edge bending. So we can fill in these values from here as a panel load. In previous versions we have already these in-plane edge loads. So this is already prepared in this example case, so let's take a look at the panel load. So what I have done is I have transferred these in-plane loads here, and now there are two new tabs, edge load bending and twisting, and this MX and MY are set here. The syntax is following that. Here in the middle of the panel you can see that the syntax based on the classical lamination theory, which is valid with these results, but when you fill in the loads you have to pay attention that they are set with respect to the global coordinate system. Okay, now I have the load vector created. The panel itself is a simple narrow laminate strip, and the panel 1 has been selected for this one, and the boundary conditions are simply supported. So now I can perform with the panel analysis a load response analysis, and what I obtain is the thermal distortion of this narrow panel, and this is due to the delta T, and this is an unsymmetric laminate, so therefore it bends like this after the curing. The magnitude of the bending matches really well with the experiment. Final words about this example. So the analysis approach is valid for flat panels and when you use a linear static analysis. The second example is related to the cell-based stiffeners, and for this one I will take another example case, and this example illustrates the cell-based stiffeners and how they differ from the traditional beam stiffeners. By default, stiffeners attached to the panels are now modeled with cell elements. And in this example, what I'm going to use the panel and the stiffener are equal in width, and in the panel there are also, in the stiffener panel, there are also transverse rib stiffeners at both ends, these red ones here. To better visualize this concept of cell-based stiffeners, I will close this one and I will take a copy from the current panel, and I make some modifications to better illustrate this one. So let's take the preview to see the stiffened panel. What I do first is I will remove these rib stiffeners from the ends, so they are Y stiffeners. First, the farmost, I will pick it and I will delete it, and the second one. And now we have only longitudinal stiffener attached to the panel. What I do next is I make the panel a little bit larger in the transfer direction. The stiffener is still attached to the very edge of the panel, and then I will a little bit move the stiffener. So now it's at the edge, then I move it to 10 millimeters. And this is now a stiffened panel model with the shell elements. Now I go to the analysis options. There's a new tab here. So by default we use now shell-based stiffeners, and if I modify that selection, I can see the old way of modeling the stiffened panel. So there are beam elements running at this level. So this level corresponds to the mid height of the stiffener. Please notice that if you have created stiffened panel models with previous ESAComp versions, and they may not be feasible in this new version, as in the previous versions, beam-based stiffener elements were used. Physical constraints for the location of the stiffener were not that tight. So now that we consider physical dimensions of the stiffener in the FE cell model, the flanges need to fit into the envelope of the panel. So it might be necessary to modify your old models. I will continue with this example and show a little enhancement in buckling analysis. So if I perform for eye profile bending, sorry, now the beam stiffeners are still active. So what I wanted to do, I wanted to use shell-based stiffeners. So there's a bending moment applied to the eye stiffener. And what I want to do next is I want to bend it into the other direction. So I take the copy of the bending load and I change the direction of the load. So I change the sign of these two load components, which are at the end of the panel. And I repeat the analysis. Side view, and now it bends to the other direction. And what I want to do is make a buckling analysis using the first load vector. I take the eye profile, I fire up the buckling analysis with the first load vector. And now the upper flanges are in compression and they will buckle, reserve factor being 1.66. Then I perform the buckling analysis with the second load vector. In this case, also the upper flanges buckle. They are in tension, lower flanges are in compression. The reason for this, that the upper flanges buckle, is that when you perform the buckling analysis, both of these load cases are considered. So the load vector the user applies and also a load vector multiplied by -1. And in this model, the lower flange also contains the panel, and it's stiffer and thicker. Upper flange is thinner, and the sign here -1 indicates that the buckling mode shape is related to the so-called reversed load vector. Okay, that was the stiffener, and I will a little bit continue with the same topic to illustrate how you can model profiles in ESAComp. And I will take a example case 42, and a preview. So in ESAComp you can make a profile, and this is this example a single cell closed profile. And in this case the blue part here corresponds to the panel, and plus the lower flange of the C profile, which is running this way. This is the web. The light blue is the web of the C stiffener. Light green is the upper flange of the C stiffener, and the yellow web is belonging to the T stiffener, where the flange of the T has been excluded. Let's take a look at the different stiffener specifications. So I will go to the beam tool, and I take the C profile, the layout. In this case, the purpose was to make a profile where the outer dimensions of the profile are 50 times 50 millimeters. The inner dimension in the height direction is 47 millimeters, so it's measured between the flanges. The flanges are 1.5 and 1 millimeter thick, so the total height of the stiffener itself is 49.5. The missing 0.5 millimeters comes from the panel, from the thickness of the panel. When you combine different stiffeners and you want to create a profile, you have to remember that or know that when the shell model is created, the nodes are placed in the mid thickness, in the geometrical midplane of this upper flange. So when you specify the other stiffener to close the profile, the height of the stiffener is specified so that you take the height of this C stiffener minus the half thickness of this flange here. So just to make sure this, we go to the T stiffener to show that the flange has been selected to be none, so there is no flange, and the web has the specific height that matches with the other profile specification. Little bit play around with this profile. So I will take the preview of the, so that you can see that the modifications. I want to make a multi-cell profile, so I will increase the width 3 times wider, bigger, and then I go to a X stiffener specification. I will move this web here to the other edge. And then introduce 2 additional C stiffeners. Did I now modify? Yes, the purpose was to add. Okay, this way. So now a profile with the multiple cells has been created. Okay, I move pretty fast to the next example, which demonstrates how we can simulate an end shortening problem of a stiffened panel. So this one demonstrates that how we can apply a uniform displacement at the edge of the stiffened panel. Let's take a figure. So we want to apply uniform displacement at the edge of this stiffened panel. And in ESAComp, generally loads are specified in terms of forces and moments. But the simulation, like in the tests, these kind of panels are tested they are displacement driven, not force driven. So we need to have a workaround for this one. And the workaround is that we define a pretty rigid small transverse stiffener here, and when this stiffener is specified here, when the loads are applied, that stiffener transfers the force so that the displacement is uniform in the axial direction. ESAComp allows to save the analysis results, and under the panel object, I have results at 3 different load levels, and saving the results is quite useful for time-consuming problems like the ones here, where geometrical nonlinear analysis with multiple substeps have been used. So I have 3 sets of results here, and I will pick the first saved results, and I view. And so these results correspond to the load level of 60 kilonewtons. And if I pick UX, I can see that the end shortening for this load level is 0.6 millimeters at the edge. And if I look at the vertical displacement, I can see that, and you can see that there are lots of small transverse wrinkles at this load level. Now we go into the end shortening force curve a little bit higher. So the load has been increased to 70 kilonewtons, and end shortening has been increased to 0.73 millimeters, and the panel skin buckling has taken a little bit different form. The third set of results corresponds to 100 kilonewtons, and now the end shortening has increased relatively large amount of the global block buckling has started, which we can see by selecting displacement in the z direction. One more thing related to this example, that if I take the copy from this panel and I will remove not the axial stiffeners, but I will remove the transverse stiffener. So this stiffener is now removed, and I make an analysis, linear static analysis with the lowest load level, and I look at the end shortening. One can see that it's not uniform because there is no transverse stiffener. A little bit magnified the displacement, so it deforms, the panel deforms more between the stiffeners. Next topic, the final topic in my presentation is composite pressure vessels. And we have two different simulation approaches available in ESAComp. And in both cases, the input data for the structural model comes from the Composicad, which is a winding process simulation software. In ESAComp version 4.5, we already introduced the shell-based simulation of composite pressure vessels, and now I'm going to highlight the enhancements of this model. So I'm going to use an existing ESAComp example, case 40, and this file includes the definitions for the materials that were used in the winding simulation. So these materials need to be defined. That's all from what you have to prepare in ESAComp. Then you go to import the files produced by Composicad from import menu. You browse to the folder where the files reside. There are 3 different files. You pick one of them and then you start the simulation. You can also set up the analysis options, select failure criteria, for example. The model itself is a medium in size, roughly 11,000 elements, and the simulation runs in 20 seconds in my laptop. So now this is the result of the failure analysis inverse reserve factor. In previous version, results were shown for all elements. Enhancements now are that you can define the range of elements for which you look at the results. So I will re-specify the laminate range, laminate 1 being at the other end and laminate 143 now at the other end. So now the range has been re-specified. That's a new feature. Then if I pick, for example, strains, surface strains, outer surface and hoop strain, the new capability is to look at the results in terms of line charts as well. You can access those from the preview. Pick and pick the item. So I will pick epsilon y at the outer surface. So now the same strain distribution is shown using line charts. New features are that we have added compensating loads here at the edge. Typically the model has some kind of round opening, so there is we calculate the area related to this opening, and based on the pressure we define a compensating load, edge load. One more thing for the shell-based CPVs is that already in the previous version you could make a point-wise post-processing. You could pick element from the model and then you could look at the stress results at that specific location using the result viewer. But now you can also take the laminate definition at this location and the load vector, and you can create them so that there are new objects created in ESAComp. So you select element and then you create laminate load. And after you have closed the viewer, you find that there is a laminate created related to the selected element and also the load vector. So you can there are more analysis options available by this way. The final part of my presentation is that I shortly show the CPV module that uses 3D solid elements. That's a new tool. And again, I use an existing example. The approach is identical to the cell-based simulation. So you need to define materials, and then materials that are in the winding process, and then you launch the simulation by selecting a folder and files containing the information that comes from the Composicad. Now in this model we focus on the cross section of the model, so it's a full 3D description of the structure, but using a sector of the model. It's not the full 360 degrees model, but a user specified sector model. In this case, I have defined the sector angle to be 2 degrees. This model had roughly 11,000 nodes, and the running time was half a minute in my laptop to give some ideas about the model. You can see the mesh here. It's quite detailed. We can look graphical results for all elements at the same time. So I want to look at the stress at the laminate coordinate system. The laminate coordinate system is defined by the axial direction of the tank and the hoop direction. I select at which level the results are studied in the middle of the element, and for example the out of plane, the shear stress is in the out of plane shear direction. Results are now for the whole model. I can focus on the specific cross section of the model by selecting from the drop down menu. Cross section 1 is now here at the other dome, but I will pick a cross section from the mid part of the model, and that's here. And what I want to show is that the strain distribution in the hoop direction. So you can see that the strain varies from the strain distribution in the hoop direction is not constant. And then one more thing, for example, the previous results were based on they were laminate based, but I can have results in a ply-wise manner. There are 36 global plies in the model. I will take the first one, and for example, that's the innermost in the model, and I look at the thickness. And when you do the ply-wise post-processing, you can have line charts available for the different plies. So now you can see how the thickness develops. It's a constant in the cylindrical shell section. Then there is some increase of the thickness when there's a turning point. Okay, more information is available for this CPV approach on a YouTube video. You can find that by subscribing the ESAComp newsletter or follow our website. And this was a little bit longer my presentation that was planned, so I apologize for that, and I please follow Andre's part as well. I will give the talk to Andre now.
Thanks, Harry. I'll try to speed up things a bit. So let's get myself presenter. And I think should be coming up any minute.
Muted.
So two topics that I'd like to cover quickly. First one is on the HyperWorks and ESAComp post-processing interface. And as you can see, I've already started out with the demo model right here. So when you're using HyperWorks 14 and the latest patch 130, then you will find the possibility to go in the preferences to go user profiles, engineering solutions, and there's aerospace as well. And when you work in this profile, you'll be able to see that magic toolbar up here, the aerospace toolbar. And the ESAComp itself, the ESAComp related features, they're hidden in the certification menu. So there you'll find the ESAComp export and ESAComp import. And the way this works is rather simple. So you hit the export button, decide for a file name what to export, and then you're asked, okay, for which elements would you like to do the export? And I'll just go and pick a pcomp in here. Then which load cases would you like to export and what kind of data? The reason for the last part, which type of data to export, is that depending on OP2 or collected OP2, H3D, collected H3D, these data items, they change. Or the names of these data items change. Fact is, what we need always are the element forces and moments. And here we got the element forces selected along with the element moments. And there it goes through all the load cases and all the data items and exports the stuff. So this is it on the first side. Maybe just to illustrate what kind of data is available in here. So you have to make sure when you're doing your solution step to have the forces and moments, the data items available that they can be exported later on. So on the ESAComp side, things are equally simple. You could just go and import the case itself. So you would go to the exported file and just import it. But if you want to do advanced failure criteria and you want to look into transverse shear, then the pcomp doesn't contain these transverse shear strength values, so you might have to add these. And for this, you can follow the process to import your stuff, make changes you want, like for example adding transverse shear strength, save your case and just get back to the materials later, because now if I do an import, set the right units, this is Newton millimetric, and use existing plies, then it's going to fall back to the plies that are already in the case. We're going to add the same capability also for laminates, because ESAComp supports more capabilities in interlaminar shear handling than what the pcomp usually does. So for ESAComp you can define the interlaminar shear strength depending on the interface, so which material interfaces with which, and not just based as one value for one laminate. So you can get a bit deeper information on that side. So when you run ESAComp, most people who have used that before will know you'll get, first of all, the list with the results, or partial list of the results that contains reserve factors, critical failure mode, critical layers, of course the loads, theta, and also the offset that was given with the import. But in the background, we already create a file that can be read into HyperView. So now if I do the same, go to certification and ESAComp import. First I select the file. Now I go to the layer results file. That's the one that we need, automatically created, as I said, in the background. And export to HyperView. That means in the background there's an HW ASCII file created that has the plywise information and can be read straight into HyperView. And then you can choose whether to import the full database or just the main information. Main information means laminate level information. That includes the reserve factors, that includes the failure mode, critical layer orientation, and ID. If you go to full database, you will have all the plywise values imported, but that can be a bit heavy for kind of spreadsheet handling in HyperWorks. So I recommend that only for a small number of elements. Okay, now we have imported the list and also already seen the file. It has been loaded to HyperView. So on the left side, we could decide, okay, I just want to see a contour of the reserve factors straight, and that shows up then still in HyperMesh. Let's rotate the model so these two are coupled. So you can see what's the laminate level reserve factor for the particular element set. You could go and like create a new worksheet and combine different data items and make new calculations. For example, create a table that creates a margin of safety or inverse reserve factor from the given values. But you can also go here and say, okay, for these three elements, I want to get some nodes created that tell me what's the failure mode and what's the critical layer ID, and that's then reference to the global ply. So if we send that to HyperView, we'll first get the magic annotations that tell us, okay, it's fiber fracture in compression. We get the layer ID, and of course we can also flip through and, for example, look at, first of all, the reserve factors. But you can also look into different layers. So if you want to check different reserve factors for the plies, then that's easily available. Yeah, so that's the quick shot for the process with HyperWorks 14 and ESAComp, and the little new things like the support of existing materials to get the materials right immediately. Don't have to go into the file and modify the stuff and rerun the post-processing. And that being said, we can swap over to the Python part. Many of you have probably not been in contact with what are the capabilities on the scripting side of ESAComp, because admittedly it has been a bit cumbersome to get around and working with the old macro language that we've been using. So we decided to swap that for Python scripting, as that's firstly rather common in the engineering world, but also rather easy to use. And yeah, to get you started, probably the easiest thing is just to have a look at the examples. So well, you usually start with the typical import case, and just to show you how easily you can implement, for example, own failure criteria. Let's look into the Hashim 2D failure criterion. The whole implementation is in the text that you can see, so it's really not much more than that. You basically just import the ESAComp module and some math module. Then you grab the stress limits and the stress components. So you tell ESAComp, okay, I want to define a failure function. Then you grab the values needed, so input and output. Input values from the forces and moments side, or actually here then in the stresses, and from the stress limits, straight from the materials, and then well you just do your implementation and create the output. So it's really rather simple to go about that. There's a few others, for example, for like random laminate creation, or also micromechanics rule of mixtures. That's like just the beginning of examples that we're going to provide. But to get an overview of what are the available functions and how do I connect these to the objects, we have included a rather complete object documentation. So basically, when you look into apply, you'll find all the different variables that are connected to the ply with a short explanation. What's the type and what's the content, and the way how to access these is explained. That was the there we go. Is in the scripting user interface documentation itself. So first of all, you find a graph that illustrates how the objects are connected with each other, and then you find a list. While this list, that list might not always be the best way to kind of scroll through things, but you can easily search, for example, something like get laminate. And so if you know somewhat what you're looking for, or you just search for laminate or for a certain property, then you're most likely going to find it. And if you rather looking at a list of just the different commands that you use, that one is available as well. So for example, you can just click to new case, and then you're going to jump to the corresponding place in the documentation. So it's rather easy and rather well documented, also compared to the old way of scripting. So last but not least, Harry already mentioned that we have a YouTube channel, and we have collected roughly half an hour explaining in detail how the solid modeling of CPVs together with ESAComp and Composicad works. So feel free to have a look there. And yeah, that being said, just some general remarks before we can swap over to some questions and answers. First of all, you all know that the 4.6 Windows version has been just released. The Linux version is coming up quite soon with a few minor enhancements and fixes in there. We usually support SUSE and Red Hat Linux distributions, so if you have something else, please let us know. We can see if there's an easy way for us to recompile on a different distribution. And also, as you can see here, the latest version is now available via the Altair Partner Alliance. So if you go to Altair Connect and you happen to be a HyperWorks lease user, you can access the latest version from there as well. Yeah, you find our contact information on the right side, but I'm sure you all know how to contact us. So right now, yeah, open the session for questions and answers. Feel free to type them in the chat box, or just unmute yourself and speak out loud. Okay, looks like for the moment we don't have any questions, so just get back to us if you have some. Let us know also what's your interest in additional features and other things. I thank you for spending your time with us, for your interest, and I hope to see you soon, coming back with interesting support questions or other things.